Okay, today we study X22NQ. You can download this PDF file. You first visit kpop.org, then you will find table of contents. You click X series, scroll down to find X22. This is main textbook. If you click this one, you will find Korean lecture and English lecture, and you return to kpop.org, then X22. You can still click this one to visit the YouTube channel, K-pop YouTube channel, to find the link for lecture. There is another file that is called X22C checkpoints, the various problems involving X22. The corresponding lecture in Korean and English are given in there. Now we are working on X22NQ, that is for the preparation of detecting the problem given in X22Q. So if you are familiar with if you do not have any difficulties to solve these problems in X22Q, then you don't have to study NQ. After finishing this lecture, I'll upload it to the K-pop homepage for YouTube homepage, and this button will alive, and you can visit there. So why don't we click this to find our homepage, the YouTube homepage for K-pop collaboration. These are shorts displaying our beautiful figures involving general physics, and you visit the playlist to find various subjects. But it is very inconvenient to select a specific video that is appropriate for you. So I recommend you click this to visit to kpop.org and look at the table of contents. For example, if you click this, you can find the classical mechanics. Okay, so let's begin. X22NQ properties of waves. It's the X22NQ. We focused on the trigonometry and the trigonometric formulas, addition formulas. So if you're familiar with them, then you don't have to study this and go ahead with the X22Q directly. List the methods to verify the addition formulas of the trigonometric functions. We are well acquainted with these formulas. Okay, there are several ways to verify these trigonometric addition formulas. First of all, we introduce a vector. This is a unit radial vector. It's xy plane. In the two-dimensional Euclidean space, you can choose the origin and draw a unit circle and choose angle alpha to be the polar angle measured from the positive x-axis counterclockwise. Then a point on this unit circle with radius 1, and this is E1 hat is the unit vector along the x-axis. E2 hat is the unit vector along the y-axis. The coordinates are cosine alpha and sine alpha. If we make use of these unit basis vectors, the unit radial vector can be expressed as a linear combination of E1 hat and E2 hat. The answer is this. Okay, we make use of this to find the cosine alpha plus beta. We remember that the scalar product of two vectors, A dot B, this is a product of the magnitudes of A and B and cosine theta, where the theta is the angle between the two. Okay, so this angle, why don't we choose this angle to be alpha plus beta? And why don't we remove this factor? This can be done by choosing the unit vectors. And why don't we choose the angle to be alpha, angle to be beta? This is x-axis and origin. What is the vector represented by this situation? And that is this ER hat, and the argument of this is beta instead of alpha, because it has been rotated counterclockwise by an angle of beta. The other vector, the other unit vector, also be expressed in terms of ER. However, we have rotated this vector from this E1 hat by an angle of alpha clockwise. Because it is clockwise, we have argument minus alpha. Therefore, cosine alpha plus beta is the angle between the two unit vectors, this and this. This is nothing but ER minus alpha, scalar product with ER beta. Why don't we substitute explicit value for minus alpha? Then we have negative sign on sine, because a sine minus alpha is minus sine alpha. Next one, we have cosine and sine, with both of them are positive sign. We make a scalar product, and we know E1 dot E1 equals 1. E1 dot E2 equals 0. E2 dot E1 equals 0. And E2 dot E2, it is also 1. Therefore, crossing terms vanish explicitly, and only E1 dot E2, E1 dot E1, and E2 dot E2 survive. The corresponding terms will be this and this. We have positive sign for cosine alpha, cosine beta, and negative sign on the sine alpha, sine beta. This one reproduces the identity for the addition formula of the cosine function. Next, we consider this addition formula for sine. Because the scalar product involves the cosine of angle between the two vectors, and the cross product of A and B correspond to the sine theta. Therefore, now we consider the not scalar product, but vector product or cross product of the two vectors. Okay. Now, still we use this. And if we have two vectors, sorry about that. If we draw two vectors, ER hat minus alpha, ER hat plus beta, and the angle from this to there is alpha plus beta. We know this scalar product, this cross product is proportional to the normal vector, and the normal vector can be obtained as E3 hat positive direction because we are rotating this vector to there counterclockwise. Therefore, because the angle between them is alpha plus beta, we have the result like that. Now we substitute these values for this and that. We make a vector product. We remember, oh, there is a mistake. This should be the cross product instead of scalar product. Okay, I just have corrected this. This is a cross product instead of the scalar product. So I have substituted these values for this and that in the cross product of the two vectors. Now we use this multiplication table. As you know, parallel or anti-parallel vectors cross product is 0. E2 cross E2 hat equals also 0 vector. However, E1 cross E2 equals E3, and E2 cross E1 equals minus E3. Therefore, cross product of these two will give cosine, cosine, and 1 vanishes. This one, E1 cross E2, that is a cosine alpha and sine beta that survives. Next, E2 cross E1. E2 cross E1 is minus E3. E2 cross E1 is minus E3. Their coefficients are sine alpha, cosine beta. Because of this, minus gives a positive sign, minus minus. So it is E3 cosine sine, sine cosine. You can find this formula with positive sign. This one, cosine alpha, sine beta, sine alpha, cosine beta. This one is reproduced if I remove the common factors. That's not all. We can also make use of the rotation matrix. We recall that this rotation matrix rotates a unit vector 1, 0 that can be expressed in terms of E1 hat after rotating this unit vector by an angle alpha counterclockwise. You will find 1, 0 gives cosine alpha and sine alpha. If you rotate a unit vector along the y-axis by an angle of alpha counterclockwise, the resultant vector component will be minus sine alpha cosine alpha. Therefore, this rotation matrix first column represents this, and the second column that can be obtained by multiplying 0, 1 is this. Therefore, for any vector x, y that can be represented by xe1 hat plus ye2 hat, this one can be rotated to any vector with xe1 hat plus ye2 hat can be rotated by an angle of alpha counterclockwise to find x prime y prime or x prime y prime or x prime e1 hat plus x or y prime e2 hat to be like that. Okay, so what about the product of these two rotation matrices? These two rotation matrices can be multiplied to find a single rotation matrix as far as we keep the axis of rotation, that is positive z-axis, to be fixed. If it is not the case, if you change the axis of rotation, then you cannot obtain this kind of relation. However, this is a series of rotation about a single fixed axis. Therefore, I find the product must be a single rotation matrix with the argument that is the sum of these two angles. So if I substitute this sum, alpha plus beta, for this alpha, what I find is a cosine, sine, minus sine, cosine, with all of the arguments replaced with alpha plus beta. What about the explicit multiplication of the two rotation matrices? So we copy them and replace this alpha with the beta. Direct multiplication of two matrices can be made by multiplying a row in the front one and column that is multiplied. Therefore, this one gives cosine alpha, cosine beta, and minus sine alpha, sine beta. What's that? Well, is it? The answer is given here. This result is reproduced. And what about sine alpha plus beta? Then we multiply this one and this one. Sine alpha cosine beta plus cosine alpha sine beta. Let's see. Well, is it? Is it this one? Cosine alpha sine beta. Cosine alpha sine beta. Sine alpha cosine beta. Sine alpha cosine beta. Plus. Okay. Perfectly reproduced. Another way to reproduce the addition formula is to make use of number. Okay, there is a mistake. It's not W. This is W equals e to the I beta. Okay, I have corrected this one. I have two complex numbers of unit modulus. The absolute value of each complex number is 1. That must be expressed as exponential I alpha and I beta, where the angle alpha is complex plane x, y, that is imaginary part plane, is identical to the two-dimensional Euclidean space. I have e to the alpha angle is this. Okay, z equals e to the alpha, then it is a unit circle. So we have cosine alpha plus I sine alpha. W that can be expressed in terms of e to the I beta should be cosine beta plus I sine beta. Sure, you must know I equals the square root of minus 1. Why don't we multiply these two numbers? Then I would get cosine alpha plus beta and sine alpha plus beta. We can expand this, but expansion of these can be found by multiplying the explicit exponential I alpha and exponential I beta. So copy this in here and we expand. We expand the real part should be cosine alpha, cosine beta, and another real part is I times I, this minus sine alpha, sine beta. That is the real part. And what is the imaginary part? That has only a single I. So single I, this product, cosine, this product, cosine alpha, sine beta, and sine alpha plus sine alpha cosine beta. So from this, we can determine the imaginary part that is sine alpha plus beta. Remember, the law of exponent, this one is the same as this, can be obtained directly from the definition of E defined by this Bernoulli's definition of the Euler number. This one can be used to prove the law of exponent by explicit expansion. So if you multiply this, and you will find, wait a second, this is not zw, this is e to the z plus w. Sorry about that. This should be z plus w. Okay, corrected. Exponential g plus w can be expressed in terms of, because e to the x can be expressed as we substitute z plus w in here, and actually it is identical to this because any term, additional terms, which is a higher order in 1 over n, except for this term, regardless of these numbers, they vanish explicitly. So I don't have to worry about adding this remnant term. And if I add these two, this one expression is factorized. And then I attach the power, distribute this power there. Then I find they are e to the z and e to the w. And I can always expand this, reorganize this sum to find the, you know how to reorganize the sum by making use of Pascal's triangle. So you can reproduce this product can be expressed in terms of a single exponential one. Okay, next. Second, by making use of the following identities, show the sum of any sinusoidal functions of the same period and the same amplitude is another sinusoidal function with the same period. It is a very, very important. First, remember a right triangle with angle of theta. We can define cosine and sine. Cosine theta equals r xy, then x over r. Sine theta equals y over r. Why don't we replace this angle? This is the theta, then this angle is half of pi minus theta. Then we have exchanged x and y. Therefore, this is sine half of pi minus theta, and this is cosine half of pi minus theta. So for any x, these are identities. They are identities. Remember, it's a property, straightforward properties of evident properties of the right triangle. Any two sinusoidal functions of the same period and same amplitude, and same period, because the wave number, this kx k determines the wavelength. So I have introduced this, and then we allow the difference in the two phases. This is a common phase, and if they are different from each other by a delta, then it can be expressed in terms of plus 1/2 of delta, plus 1/2 of delta, and minus 1/2 of delta. And this is a common phase. All right. So why don't we define this one by alpha and define this by minus beta? And then the psi 2 can be expressed in terms of sine alpha plus beta. We know the addition formula for sine, this one and this, and if I add them up, we have these two cancel, and this is doubled. Okay, so doubled vector. This one is beta. This beta was a what? Beta was 1/2 of delta. Phase difference, half of a phase difference, 1/2 of phase difference of the two waves. So this one appears 1/2 of delta, and then remaining piece is alpha, the common kx plus delta. So kx plus delta appears as common, and cosine 1/2 of delta appears as common. Finally, the resultant wave, this one has kx, this one has kx, this one kx. All of them may differ in the phase. An interesting thing is that we have found an additional factor, that is factor of 2, coming from the addition of 2 multiplied by cosine of 1/2 of delta. That is the phase difference between the two. It is a very, very important to understand the nature of interference. Sometimes they are doubled, sometimes they cancel exactly. Interpret the following figure. Yes, depending on this phase difference, now delta is replaced with phi. 1/2 of phi appears in the case of two-dimensional vector addition. We find the rhombus, the the magnitude, the length of the two sides are the same, and the diagonal of this rhombus is nothing but this, because these two are of the same length, and we draw a line bisecting the angle that phi. This is a phi phase difference, the angle between the two vectors. This angle bisecting this angle is just 1/2 of phi, and then you arrive at cosine, cosine. So this is the original amplitude, and the contribution along this diagonal is this, but another contribution coming from this guy makes this length doubled. So that is the 2 times cosine, half of this angle. This is also equivalent, can be understood by making use of complex number unit modulus. So both of them are equivalent. When they are added up, depending on this phase difference, when they are opposite, 1/2 of phi equals a right angle, of phi equals 2 pi, phi is pi, the back to back. In that case, it is completely destructive. If they do not have any angular difference, that with phi equals 0 or 2 pi, in that case, they make the amplitude twice. That is called fully constructive. Okay, that's it for today. Thank you.